Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into a fascinating and frankly, a little frustrating topic. Why do multi-agent LM systems fail?
Frustrating is definitely the word. I mean, we've got these incredibly powerful large language models, right? Capable of generating text, translating languages, even writing different kinds of creative content. You'd think scaling that up to multi-agent systems would be relatively straightforward,
But it's not. And I think the why is a lot more fundamental than just scaling issues. We're seeing these systems fall down in ways that suggest a real lack of understanding, not just a lack of processing power.
Exactly. They can sound convincing, they can even appear to collaborate on the surface, but when you dig a little deeper, the coherence falls apart. They lose track of the bigger picture, make illogical leaps, and generally fail to demonstrate the kind of common sense reasoning you'd expect from even a rudimentary collaborative effort.
So, let's unpack that a bit. Otto, you've been pretty optimistic about the potential of deep learning to achieve AGI. Do you think these failures are just a bump in the road, solvable with more data and bigger models?
well, I wouldn't say just a bump in the road. I think they highlight some crucial limitations in how we're currently approaching multi-agent coordination. But I still believe that deep learning, with some key advancements, holds the key. Think about it. These LLMs have learned complex patterns in relationships from massive amounts of data. They've essentially internalized a vast amount of world knowledge, albeit in a distributed, implicit way. The challenge now is to figure out how to effectively coordinate these agents and incentivize them to work together towards a common goal.
See, that's where I disagree. I think relying on purely statistical associations, which is what deep learning fundamentally does, is insufficient for true understanding and reasoning. More data might improve performance on specific tasks, but it doesn't address the underlying problem, the lack of explicit knowledge representation and symbolic manipulation. They are all associations without knowledge, a memorization system at best.
But isn't that a bit harsh? They're not just memorizing. They're learning intricate relationships, complex dependencies that would be impossible to hand code. They can generate novel text, translate between languages, even answer complex questions in a coherent manner. Surely that's more than just memorization.
I think it's somewhere in between. It's not pure memorization, but it's also not the kind of flexible, generalizable reasoning that we associate with intelligence. I suspect a big part of the problem is their handling of space and time. These systems often lack an explicit model of how things change over time and how different agents relate to each other spatially. They are not properly using the information around them.
That's interesting, Donald. So, you're saying their understanding of the world is fundamentally limited by their inability to reason about spatiotemporal relationships.
Exactly. Imagine you're trying to explain to two LLM agents how to build a tower out of blocks. One agent might understand the concept of stacking in a general sense, but if it doesn't have a clear understanding of the physical relationships between the blocks, where they are in space, how they're oriented, how they need to be moved, it's going to struggle to actually build the tower. And if the other agent has a different internal representation of space, or a different coordinate system, they're going to have a really hard time coordinating their actions.
That makes sense. It's like they're speaking different languages, even if they're both using English words. The underlying concepts, the way they're representing the world, is fundamentally different. This is where the neuro-symbolic approach comes in, right? We need to give these systems a way to explicitly represent knowledge and reason about it in a more structured way. It's the same as building a house with specific instructions versus throwing materials in a space and hoping something useful comes out.
Could you elaborate on the neuro-symbolic approach for our listeners who might not be familiar with it?
Sure. Neuro-symbolic AI aims to combine the strengths of neural networks, which are good at learning patterns from data, with the strengths of symbolic AI, which is good at representing knowledge and reasoning logically. So, instead of just feeding data into a neural network and hoping it learns something useful, you would explicitly define the concepts and relationships that are relevant to the task. You then use neural networks to learn the parameters of these symbolic representations, or to guide the reasoning process. It's about giving the system a scaffolding of knowledge and logic to build upon, rather than just relying on brute force pattern recognition.
But isn't that incredibly complex and difficult to scale? One of the big advantages of deep learning is its ability to learn from raw data without requiring a lot of hand engineering. If we have to manually define all the concepts and relationships, aren't we just recreating the AI winter of the 80s and 90s?
That's a valid concern, but I don't think it's an either/or situation. We don't have to completely abandon deep learning. We can use it to learn the lower level features and patterns, and then use symbolic reasoning to combine these features into more abstract concepts. Think of it like this. Deep learning can handle the perception, while symbolic AI handles the cognition.
And to tie that back to the spatiotemporal reasoning, Maybe we can use deep learning to learn how to translate between different coordinate systems, and then use symbolic AI to reason about the relationships between those coordinate systems, so the agents understand how their perspectives differ and relate to the overall environment.
Okay, I see where you're going with that. So it's not about replacing deep learning, but about augmenting it with more structured knowledge and reasoning capabilities. But even then, how do you ensure that the symbolic representations are consistent with the real world? How do you ground them in sensory experience?
That's a critical point. The grounding problem is a huge challenge for symbolic AI. How do you connect the abstract symbols to the real-world objects and events that they represent?
There are several approaches to that. One is to use multimodal learning, where the system learns to associate symbols with different types of sensory input, visual, auditory, tactile, etc. Another is to use embodied AI, where the system interacts with the world through a physical body, allowing it to learn the meaning of symbols through direct experience. And there are a lot of advancements in areas like knowledge graphs, which allow you to add relationships between pieces of data, allowing agents to reason with this information.
So imagine a multi-agent system that's tasked with cleaning a room. Each agent would have its own set of sensors and actuators, and it would use deep learning to process the sensory input and identify objects like table, chair, dust bunny, etc. But then it would use symbolic reasoning to figure out how to coordinate its actions with the other agents to efficiently clean the room. For example, one agent might be responsible for vacuuming the floor, while another agent is responsible for dusting the furniture. This could involve tasks like move the chair, pick up the object, vacuum the floor, all needing understanding of their current position in space and time.
And the agents would need to be able to translate between their own internal coordinate systems to understand where the other agents are in relation to themselves and the objects in the room. So, if one agent sees a dust bunny behind the chair, it needs to be able to communicate that information to the other agent in a way that the other agent can understand, even if they're looking at the chair from a different angle.
This is fascinating. So, it's not just about having more powerful LLMs. It's about rethinking the fundamental architecture of these multi-agent systems to incorporate more structured knowledge and reasoning capabilities, and to ground them in sensory experience and spatiotemporal understanding. But even with these advancements, what about the problem of long-term task completion? These systems often struggle to maintain context and coherence over extended periods of time.
That's a tough one. Current deep learning models tend to struggle with long-range dependencies. They can easily lose track of what happened several steps ago, which can lead to inconsistencies and errors in reasoning. One approach is to use attention mechanisms, which allow the model to selectively focus on the most relevant parts of the input sequence. But even with attention, it can be difficult to maintain a coherent representation of the entire task over a long period of time.
This is where the symbolic approach could really shine. By explicitly representing the goals, subgoals, and dependencies of the task, we can give the system a framework for maintaining context and planning its actions. Think of it like writing an outline for a long essay. The outline helps you stay on track and ensure that your arguments are logically consistent. We need to give AI systems a similar kind of framework for managing complex, multi-step tasks.
And perhaps the outline itself could be represented in a spatiotemporal framework, with each step of the task mapped to a specific location in space and time. This could help the system visualize the task as a whole and understand the relationships between the different steps. Imagine a Gantt chart, but for AI.
That's a compelling analogy. So, we're talking about combining the pattern recognition capabilities of deep learning with the structured knowledge representation of symbolic AI, and grounding it all in a robust understanding of space and time. But what about the role of neuroscience in all of this? Are there insights from the brain that could help us design more intelligent multi-agent systems? I think there are huge opportunities there. The brain is, after all, the ultimate multi-agent system. It's composed of billions of neurons that are constantly communicating and coordinating their actions to achieve a wide range of goals. By studying how the brain handles sensory integration, contextual awareness, and long-term task completion, we can gain valuable insights into how to design more intelligent AI systems.
For example, the brain uses a hierarchical organization to process information. Lower-level areas, like the visual cortex, are responsible for processing basic sensory features, while higher-level areas, like the prefrontal cortex, are responsible for more abstract reasoning and planning. We could potentially apply a similar hierarchical structure to multi-agent systems, with lower-level agents responsible for handling sensory input and higher-level agents responsible for coordinating their actions.
And the brain also uses a variety of different memory systems to store and retrieve information. Short-term memory is used to hold information temporarily, while long-term memory is used to store information for longer periods of time. We could potentially use similar memory systems in AI systems to improve their ability to maintain context and perform extended computations.
And the brain is constantly translating between different coordinate systems. For example, when you reach for an object, your brain needs to translate the visual information about the object's location into motor commands that control the muscles in your arm and hand. We could potentially learn from these neural mechanisms to design AI algorithms that can seamlessly switch between different levels of abstraction and coordinate systems.
So, it sounds like we're advocating for a more holistic approach to building multi-agent systems, one that combines the strengths of deep learning, symbolic AI, and neuroscience. But what are some specific research directions that we should be pursuing in the near future?
From a deep learning perspective, I think we need to focus on developing more effective methods for handling long-range dependencies and temporal reasoning. This could involve exploring new attention mechanisms, recurrent neural network architectures, or even entirely new learning paradigms. I'd also love to see more research into how we can extract the implicit knowledge that's already embedded in these large language models and make it more explicit and accessible.
From a neuro-symbolic perspective, I think we need to focus on developing more robust and scalable methods for representing knowledge and reasoning logically. This could involve exploring new knowledge representation formalisms, reasoning algorithms, or hybrid architectures that combine neural networks and symbolic systems. I'm particularly interested in research that explores how we can ground symbolic representations in sensory experience and build systems that can learn and reason in a more human-like way. So, really trying to find the places where these techniques merge.
From a spatiotemporal perspective, I think we need to focus on developing algorithms that can explicitly model space and time, and that can seamlessly translate between different coordinate systems. This could involve exploring new geometric deep learning techniques, spatial reasoning algorithms, or even biologically inspired models of how the brain processes spatial information. Finding a way to get multiple agents to see the same world consistently is paramount.
And from a neuroscience perspective, I think we need to continue studying how the brain handles sensory integration, contextual awareness, and long-term task completion. This could involve using techniques like fMRI, EEG, and single-cell recordings to understand the neural mechanisms underlying these cognitive processes. I am interested in looking into the specific interplay between brain regions and cortical hierarchies to get a better idea about the right framework for multi-agent collaboration.
There's also the ethical considerations. As we build more and more powerful AI systems, we need to think carefully about how they're going to be used and how to ensure that they're aligned with human values. Multi-agent systems in particular raise complex ethical challenges, as they can potentially be used to automate decisions that have significant social and economic consequences. How do we ensure that these systems are fair, transparent, and accountable?
That's absolutely crucial. We need to be proactive about addressing these ethical challenges rather than waiting for them to become a problem. This means developing ethical guidelines, regulations, and technical safeguards to ensure that AI systems are used responsibly.
And it also means fostering a broader public dialogue about the potential benefits and risks of AI, so that everyone has a voice in shaping the future of this technology. We can't just leave it up to the experts. The impact of AGI will touch every part of society, so we need to involve everyone in the conversation.
Well, this has been a really fascinating and insightful discussion. It's clear that building truly intelligent multi-agent systems is a complex and multifaceted challenge. But it's also a challenge that's worth pursuing. By combining the strengths of different AI paradigms and drawing inspiration from the brain, we can potentially create systems that are far more capable and adaptable than anything we have today. Thank you all for joining me, and thank you to our listeners for tuning in to Cognitive Spirals.